There we go. All right. Okay, so like I said, Unit 7, you'll notice the title, Differential Equations and Other Miscellaneous Calculus Topics. They really very much are kind of standalone topics. Not a lot of it is new calculus. It's more application of calculus. Okay, so no new integration except one new integration technique, but mostly they're all just kind of individual miscellaneous topics that didn't really go with anything else. And so this is where the course planners put them when they planned the course years ago. Trapezoid rule, watch the video. What the trapezoid rule is, just to let you know if you haven't had a chance yet, is another way of approximating an integral, but instead of using rectangles, you're going to use trapezoids. Okay, it's a more exact method. And really all you need to know is the formula for area of a trapezoid is 1/2 base 1 plus base 2 times the height. There are several problems in the book for you to practice. We'll practice it again together a little bit later in the unit, but please make sure that you watch the video. Somebody asked me the other day, how do we know which method to use? How do we know whether we're supposed to use rectangles or trapezoids? We'll always tell you. Okay, it's not a guessing game. We'll tell you, approximate the integral using right-hand Riemann sum, or approximate the integral using the trapezoid rule. We'll always tell you, so no surprises. And same with College Board, they'll always tell you also. All right, so our next topic, separable differential equations, is the biggest topic in the unit. From an AP exam perspective, it is the most important topic in the unit. And I say that because there's often one entire free response question on the AP exam devoted to differential equations. Differential equations, if you're interested in studying engineering in college, you'll actually take a course in college, an entire semester course devoted entirely to differential equations. It might be even called differential equations. It might be called College Math 4. It depends on the university that you go to. We are doing day 1 of that course right now, okay? And then the course goes on and it'll blow your mind. It's a challenging course. It is the course that colleges say is the weed out course from the engineering programs. Okay. But separable differential equations is the one type of differential equation we study in Calc AB. It's not really hard because it's an application of the calculus that you've learned, not a new method of doing calculus. We do a couple different things with separable differential equations, but before we do those things, we got to be clear on what is a differential equation. For our course, it's an equation that will be in X and Y. When you go to college, they'll add Z, okay? They'll take it into the 3rd dimension. It'll be multivariable. In our course, we're just still in the X and Y plane, okay? It's a differential equation in X and Y that involves X's, Y's, and derivatives of Y. Okay, so you're looking at an equation. That equation may have an X in it. It may have a Y in it. It'll definitely have some derivative of Y in it. And you can see we've already looked at differential equations before. We just never called it that, but this is an example of a very simple differential equation. You've seen that before. You've seen this equation before. You've created this equation before when you took the derivative of x squared. Okay, that's the differential equation y prime equals 2x. Very basic one. Here's a more complicated one. You've never seen anything like this before. We've never really looked at equations that have both a second derivative and a first derivative in it. Okay, but this is another type of differential equation. This is the type that you'll be working with in the college level class, not necessarily in this class. Differential equations are used to model situations such as population growth. We'll actually be looking at that model. Exponential growth and decay, we'll be looking at that model. And if you've taken physics, Newton's law of cooling, differential equations are used to model that as well. We'll also be looking at a problem later on in the class involving Newton's law of cooling. All right, so a couple different kinds of questions that you need to be able to answer with respect to differential equations. And the first type of question might be, what is the order of the differential equation that you're given? That's an easy question. The order of a differential equation is just determined by the highest order derivative that you see in the differential equation. I'm going to abbreviate differential equation like this for right now. If you don't mind, you can abbreviate it as well. So in the two examples that I gave you above, this is a first order differential equation because the biggest derivative that you see there, or the highest order derivative that you see there, is the first derivative. And then, of course, this other example of a differential equation that I gave you is a second order differential equation. Okay. So you just, super easy, you just look at the differential equation that you're given, look for the highest degree, and that's the order of the derivative. All right, so we're going to be doing two other things with them, the differential equations in this class. First of all, we're going to be doing like little mini proofs. Now, don't let that word scare you. It's really easy. What you're going to be proving is that a particular function is a solution to the differential equation that we give you. The other thing that you're going to be doing is you're going to be solving. In other words, you're going to be finding the solutions to the differential equation. All right, so let's talk about what is a solution to a differential equation. Well, a solution is going to be a function. If we say solve the differential equation, you're not looking for a number, you're looking for a function, okay? A function is a solution to a differential equation if the differential equation, this is a lot of writing here, so I'll go kind of slow. If the differential equation, equation is satisfied. All right, well, that's not the terminology I would use. I would just use it's true. It's a true equation. It's really equal. One side is really, truly equal to the other side, okay? So a function is a solution to a differential equation if the differential equation is true when y and its derivatives from the function, okay, I'm going to put that in parentheses. Okay, so you're going to be identifying two things. You're going to be identifying which is the function, which is the differential equation. You'll see that in a minute. So you're going to substitute y and its derivatives from the function that you're given, okay, are substituted. You're going to substitute those into the differential equation. Okay, so that's what a solution is. It's a function. So the tricky part is you're actually dealing with two different equations. You're dealing with a derivative equation, a differential equation, and some function. And you're trying to determine the relationship between the two. You'll see how we do that in a minute. All right, so let's start with that most basic differential equation that I gave you. You can tell me what the solutions to this differential equation are simply by anti-differentiating. Some are as easy as that. Okay, so the general solution to this differential equation, this is the differential equation, is y equals x squared plus c. This is called the solution. So sometimes a solution is found simply by integrating. There aren't going to be very many of those. Those are way too easy. You've already done a lot of integrating. We're going to show you how to do more complex ones. Okay, but it is definitely a solution. It meets this requirement for being a solution. What is that requirement? Well, that requirement is that you take the y and its derivatives and substitute in here to see if it becomes true. Well, there's no y to substitute in here. There's only a y prime and an x, but there is a y prime. So I find y prime of this, okay? And that, in fact, makes the differential equation true when I substitute this in there, okay? So when you're dealing with a simple equation, it's hard to, make this make sense. I'm going to make this whole thing make sense in a more complicated example, but just know in your most basic differential equation, your solution is found by anti-differentiating. That's all you need to know here. Okay. All right. Also, another thing I need to teach you is a little bit of terminology. This right here, this x squared plus c, is called the family of solutions to the differential equation y prime equals 2x. Okay. You'll probably never hear me say that again, but we have seen that terminology in a FRQ question in the past where it just says, let y be a function that's in the family of solutions to the differential equation. So I just wanted it to not be the first time that you've seen that. The reason for that is many differential equations have more than one solution. This one does. Y prime equals 2x has the solution x squared plus 9. It has the solution x squared minus 100. It has the solution x squared plus 1/4. Okay? Differential equations have many solutions, and when you group them together, it's called a family of solutions. Okay? That's probably the last time you'll ever hear that again until you go on and take a differential equations class in college, if you do. All right, now we're going to work with another more complicated example where I'm going to show you the first type of more advanced question that you might be asked. This is the prove question. This is where you're doing a little proof. Okay, and again, don't panic with the word proof. It's not like in geometry. If you did proofs in geometry where you're doing a T-chart and all that, you're not doing that, okay? So here you see the words show that. That's an indication that this is a proof type problem, okay? Other ways that you might be asked the same question. So other ways this question may be asked. Let's put that over here, just so you are aware. other ways this question may be asked. Okay, so the first way, of course, is show that. Another way of saying show that is prove. Okay, and then a third way might just be is. Okay, is this function, whatever function they give you, a solution? Okay, so 3 different ways that question might be asked. You tackle that question, these 3 questions, all the same way. All right, so our job is to show that this is a solution of this. Your first thing that you need to do is decide which of those is the differential equation. It's obvious because only one of them has a derivative in it. Okay, so this is the differential equation. And this is your function. Okay, so we're trying to show that this function is a solution to this. Well, the way you do that is to decide, is the differential equation true when y and its derivatives from the function are substituted into the differential equation. So we're substituting into this equation. This is the equation we're substituting into. We already know what we're going to plug in here for y, because we know what y is. We don't know what we're going to plug in here for y prime yet, but we can figure that out because we can find y prime. So let's do that. If y equals ce to the negative 2x, then y prime equals, oh, this is a derivative from first semester. The derivative of e to the u is e to the u prime, right? It's a box method, okay? Box method. So we're going to do e to the u prime. What about the c? Well, that's just a constant. We know constants come along for the ride, okay? So the derivative of e to the u is e to the u times u prime, and that c was there to begin with, so it comes along for the ride. Okay, so that says negative 2c e to the negative 2x. All right, we now have everything that we need to plug into this equation to see if that equation is true. Okay, so this is substitute y prime and y into this to determine if it's true. Does it make a true equation? All right, no problem. Let's see. Y prime is negative 2c e to the negative 2x. That's y prime. Plus 2 times c e.
Miss O'Toole, could you move it up?
Thank you. There we go. Plus 2c e to the negative 2x. This is 2y. Okay. And is that equal to 0? Okay. All we've done is substitute into our differential equation. And I think you can see that, yes, absolutely, this side is equal to 0 and that side's equal to 0. So it's a true equation. Okay. That's it. That's your little proof. That's your little show that the function that you were given is a solution to the differential equation that you were given. And so you might just write one final sentence. Y equals ce to the negative 2x is a solution. Now, if you got something that was not true, you'd say it's not a solution.
If it says show that, it's always going to be true, right?
Yes.
Okay.
It would be, no, it's not if the question was proven this, question was asked this way. Is it a solution? Okay, but you're right. If it says show that or prove, it will be. You just have to go through the proof. Okay. Okay, now notice that original differential equation is not something we could have anti-differentiated because there's no x's in it. It's not like y prime equals 2x. Okay, so finding the solutions of that are impossible. We could not find them. Okay, the most we could do with this is if we're given something, determine if it is or is not a solution. Okay. All right, any questions so far? So the beginning part of the homework assignment has questions like this, where you're either asked to show that or determine if something is or is not a solution. And we'll practice that more together in class as well as the unit goes on. Okay, all right. So the next thing that we're going to be doing with these, and this is the most common type of question that you're going to see, is actually solving them, finding the solutions. Given a differential equation, figure out what the solution is. Okay? And you're only going to be able to do that for one type of differential equations. There's lots of different types of them, and we're going to be dealing with, in Calc AB, a differential equation called a separable differential equation. Okay, so a separable differential equation is always a first order. In other words, the biggest derivative is a first derivative. Okay, and that derivative, okay, that derivative dy over dx can be factored as a function of x times a function of y. In other words, dy over dx can be broken apart into one function in terms of x only and another function in terms of y only. Okay, now sometimes that's kind of in disguise as a rational function or a function that's a fraction. But of course, those types of functions can be broken out into the product of one function that's only in terms of x and another function that's only in terms of y. Okay, so if you can look at a differential equation and see that they're either in this form or this form, it is separable, and you will be able to solve it. You will be able to figure out what the solution to that differential equation is. So first of all, let's practice identifying which are separable and which are not. This one, of course, is. This is a separable differential equation because I can break it out into a function that's completely in terms of x times another function that's completely in terms of y. So this one, yes, it is. Okay. How about the second one? Well, in order to answer that question, we need to get this alone. Okay. In order to answer this, we want to get this piece alone. That's easy to do. We're just going to divide both sides by x squared minus 9. So if I do that, I get xy over x squared minus 9. And can I break that out into a function that's completely in terms of x times a function that's completely in terms of y? I see some people shaking their head no. The answer is yes, right? I can break this out into dy over dx equals x over x squared minus 9 times y. There it is. one function in terms of x only, another function in terms of y only. Okay, so this one, yes, it's a separable differential equation. How about 3? Can you figure out any way to separate the x's and the y in number 3? Any way at all? No. Yeah, that can't be separated. Okay, this is a no. That's a no as it is written. Okay, but I'm going to say if this had been written like this, if this had been the function, that one is separable because you can factor out the x. Okay, so always be looking at a way to manipulate. Okay, so if it had been this way, that would have been a yes. But in its original form, no. And how about number 4? Is 4 separable? I see a lot of people shaking their head. Yes, of course it is, because I can break that out into e to the y plus 1 times 1 over x. Okay, so if they're separable, then we can solve them. We can find a function that is a solution to that differential equation. So let's go ahead. Like I said, I'm not teaching you new calculus. I'm teaching you a new process. All the calculus is the same. Okay, it's just a process for solving, okay, a first order separable differential equation. All right, this first step is if the derivative portion is written as y prime, rewrite it as dy over dx. Okay, so this one is written as y prime. We're going to start with step 1, changing that notation to dy over dx equals x squared plus 2 over 3y squared. Okay, so step 1, we're done. Step 2 is the most important step. If you get this step wrong, everything will fall apart after here. So take this step slowly. Students often kind of get a little like, oh, I'm good at this part, and they go quickly and they don't separate it right. So slow down a little bit here. This part, separate the variables. What I mean by that is get all the x's with dx and the y's, I don't like the way I wrote that, with dy. Okay, so I'm going to change this. Get the x's with dx and the y's with dy. All right, so let's do that with this problem right here. We're going to do step 2 with this problem right here. Often the best way to start, cross multiply and see what happens. So I'm going to cross multiply, and in this particular problem, it works out for me. When I cross multiply, I get 3y squared dy equals x squared plus 2 times dx. Okay, great. Everything's separated. Y's are with dy, x's are with dx. Okay, so step 2 done. Step 3, now you're going to integrate both sides. No new integration technique. These are the same integration techniques that we've been doing in this class. This one, straightforward reverse power rule. If I integrate this, I increase the exponent by 1, divide by the new exponent, and that just becomes y to the 3rd. Okay, now I'm going to add a plus c on this side as well. We'll talk about the plus c thing in a minute because it's talked about right here. And then on the other side, I'm going to anti-differentiate again So this is an equal sign, not a plus sign. Okay. Anti-differentiate, I get x to the third over 3 plus 2x, and then plus c. But for right now, I'm going to distinguish between the two c's because they're different c's. Okay, one c is on the y side, the other c is on the x side. Okay, I'm going to come back to this part, add the c to one side. We'll talk about why I added it to both sides in this problem. All right, now the fourth step, solve for y if possible or necessary. Cross off the or necessary, okay, because it's always necessary if it's possible. Okay, so solve for y if possible. If it's not possible, then you don't do it. All right. So the first thing I'm going to do for when I solve for y is I'm going to subtract C1 from both sides. Well, a constant minus a constant is another constant. Okay? And so that's why when it says integrate both sides and add c to one side, that's why we only have to add it to one side, because we're going to, if we add it to both sides, we're going to end up combining them anyway. So for every problem that you see me do from now on, I'm going to add c to one side only, and I'm going to add it to the x side. Okay? So you'll never see me do this again. Okay? Don't have to do that. All right, so I get y cubed equals x to the third over 3 plus 2x. Those two constants combined is another constant. I'm going to just call it c this time. And now I'm going to take the cube root of both sides. And I'm going to do it using an exponent. You could do it if you wanted to using the cube root symbol, but I like using the exponent better. Okay, and so that function is a solution to this differential equation that included x's and y's and derivatives of y. We could prove it to ourselves. We could prove that this was a solution, okay, by going through the process that we went through on the previous page, but we're not going to do that. But if you wanted to prove to yourself that that does work, you would substitute y into the denominator here. You'd find y prime and substitute it in there and see if it made that differential equation true. So you can check your work on these, okay? But if you're good at integrating, it's really not necessarily necessary to check your work. Okay. All right, any questions there? So did we go through step? Yes, we went through step 4. We did that. All right, there is a 5th step, but we aren't going to do it on this problem because we don't have an initial condition. Initial condition, you've seen them before, they have to give us a point, an x and a y value that satisfies the equation so that we can calculate what this c is. We'll do that in our last example of the day, example 4. Okay, let's turn the page. Any questions so far? All right, turn the page. Let's do example number 2. Okay, example number 2, solve. First step's done for us. It's not written as y prime. It's already written as dy dx. So our job is to solve for this and separate first. So if you get in the habit of cross multiplying first, after you cross multiply, you'd actually have this, which isn't going to work for you. That's not separated. You have x's with dy and y with dx's. So you might then divide both sides by 2x plus y, and then also divide both sides by y. However you make it there, I don't care, okay? Whatever process you go through to getting them separated is fine with me, okay? But ultimately, this is the separation, that we want to end up with. 1 over y dy equals 1 over 2 plus x dx. Okay, so now that they're separated, separate, integrate. Okay, so integrate. All right, go ahead and integrate that, everybody. That's not new. All right, so that's how that integrates. 1 over y integrates into the natural log of the absolute value of y, and 1 over 2 plus x dx integrates into the natural log of the absolute value of 2 plus x plus c. Okay, I think this one for most people, pretty straightforward. This one, maybe you used use substitution on, you don't have to, but remember that when you're using use substitution on a fraction, it's often best to first let u be the denominator, and then du equals dx, and so this just becomes the integral of 1 over u du, okay, which does integrate back to that. All right, separate, integrate, solve for y if possible. Is it possible to solve for y? Is it possible to get y alone? Is it possible to get that y out of that natural log? The answer is yes. We actually, yeah, I see some of you shaking your head. We actually did this last week sometime when we were doing some problem. I don't remember what the problem was, but the way that you do that is you make that an exponent on the e. Okay, you make natural log of the absolute value be an exponent on the e, and then the natural log of 2 plus x plus c be an exponent on the e. Notice I put parentheses around that. The c is also part of that exponent. Some students make the mistake of just making the natural log part of that exponent. That's not correct. The entire thing has to become an exponent. Okay, now when I deal with that, this, the e and the natural log cancel, and I'm left with the absolute value of y. Now look what I'm going to write for the next one. Okay, I can't just cancel this out because of this plus c at the end. So what this becomes, and we'll explain why in a minute, it becomes e to the c times the absolute value of 2 plus x. How did I get there? There's a little intermediate step there, okay? And I'll do that little intermediate step over here in green, okay? So this right here, I'm starting with e to the natural log of the absolute value of 2 plus x plus c. That's the same thing as e to the c times e to the natural log of the absolute value of 2 plus x. That's using the laws of exponents. When you multiply with the same base, what do you do with the exponents? You add them. So to break apart an exponent that's added, you create a multiplication problem. And you have to do that in order for the e and that natural log to cancel out. Okay, and so that's how I ended up with this side of the equation. All right, so that's a little review of accelerated algebra 2 there. All right, now I haven't solved for y yet, by the way. It's not solved for y until the y is all by itself, and it's currently not. It's inside the absolute value function, but that's an easy thing to fix. You just remove the absolute value signs, and on the other side, you do the plus or minus e to the c times 2, the absolute value of 2 plus x. Okay. And that's how you handle getting rid of the absolute value sign when it's there. All right, I'm going to show you one other way you might see this written on the College Board, by the College Board. This is where you're going to stop for me. I don't want you to go any further. Okay, but sometimes on the multiple choice questions, I don't know why, they do this weird thing where they write it like this. I don't know. Why can't they just leave the e to the plus or minus e to the c there? I don't know. I guess they just want to, identify that e to the c is a constant. It is. E is a number, c is a number, and a number raised to another number is a constant. I don't know why they do that. But you guys, you can just stop right here. I just show you that so that doesn't confuse you when you get to the AP exam. Okay? It might make you pause a minute and then you go, oh yeah, Miss O'Toole told me they do this weird thing. Okay? All right. So you're going to do number 3. It's step 1's done for you. We already wrote it as dy over dx. So you're going to separate, integrate, and solve. Okay, so go ahead, work through number 3. Some of you will have to do u substitution. Once you've separated, just do a quick check to see if you did it right, because no point moving forward if you haven't. Just check my paper. Easiest way to integrate the y side is u substitution. Okay, so check your work. Now you might notice some differences between what you did and what I did. What happened when I did the E thing? That's what I call it. It's not very mathematical, but when I did the E thing, what happened on the Y side? What did I do differently in this problem that I didn't do in the problem before? Something's missing. What's missing?
The absolute value.
Yeah, do I need the absolute value there? What's true about y squared plus 1?
It's always positive.
Yeah, it's always positive. Okay, unlike y, which could be positive or negative. Okay, so we talked about that when we did the, I could have even left off the absolute value symbols here, right? I could have left them off at this point. I could have said, okay, that's the same thing as the natural log of y squared plus 1. Okay, because if it's always positive, we don't need the absolute value symbols around there. The reason we need the absolute value symbols around there, if it could be negative, is you can't take the natural log of a negative number. Okay, and so it's just, if you don't need them, it's easier to make them go away, okay, when you're solving. Okay, and then I would accept either answer. Okay, e to the c can just be changed to a constant if you want to, just to kind of make it look cleaner. Okay, or you can just leave the e to the c in there. Okay. All right, questions on that? Okay, so no new calculus, just a different process. All right, let's do number 4. Now, number 4 has an initial condition, so our final answer will not have c in it. You're going to use this initial condition to calculate what c is. And we know this is a little confusing notation. We're not used to seeing it like that. We know that the number inside the parentheses is always your x value, okay? And then that is our y value. All right, so go ahead, take it up to the point right before you use the initial condition, and we'll pause there and make sure we agree, and then we'll move forward from there. So separate and integrate. Okay, so there is the separation and the integration. Okay, and so now I'm going to use the initial condition right at this point to find c. I always find C before I solve for Y because it's often easier. You can solve for Y first and then calculate C, but I'm just going to do it right here. So wherever I see a Y, I'm going to put pi. So that's going to be the sine of pi plus 5e to the pi. That's substituting pi in for Y equals, I'm going to substitute 0 in for x, and that just becomes 0. It's gone. Plus the cosine of 0 plus c. Okay, and now I solve for c. Sine of pi is also 0. Okay, so that's gone. Cosine of 0, that's the same thing as 1. So I'm going to move that 1 to the other side, and I calculate that c is equal to 5e to the pi minus 1. Okay, and now I'm going to rewrite my solution with c added in. Okay, now we have to ask ourselves the question, can I solve for y? Okay, well, I can't, because there's no way I can get the y out of the sine function and out of the exponent at the same time. Okay, now, if this term wasn't there, if the sine term wasn't there, if it was just 5e to the y equals that other thing, I could solve for y. Okay, I do the opposite of what I did with the e thing. I don't do the e thing, I do the natural log thing. Okay, but I'd have to move the 5 over to the other side and then take the natural log. You'll see some problems. The reason I'm telling you this is you'll see some problems later that's how you have to solve for y. You have to do the natural log thing. If this term wasn't there, if it was just sine y equals that, how do I solve for y in that case? Anyone know? You take the inverse sine of both sides. The inverse sine of the sine of y is just y, and then you'd have the inverse sine of the entire other side. Okay, and you'll run into some problems where you have to do that as well. So I'm bringing it up now. In this case, though, there's no way to solve for y, so we'll just make sure that we state that you don't have to write this down if you're doing a problem for me or the College Board, but we'll put it in our notes just so that we know that we addressed it. No way to solve for y. So we are done. And we are done not only with this problem, but with the notes for today. So if you have any questions on anything that we did, you can stay here in class and ask. Otherwise, I'm going to wish you a free, good weekend. I love you guys, and I'll see you guys on Monday. Have a good weekend.
Thank you.
Thank you.
You're welcome. Bye-bye.
Well, sorry, I didn't mean to leave. I actually had a question for you.
Yeah, good. I'm glad I didn't get out of here yet.
Okay, this is from a while ago, but I have an 8 out of 10 on the AP Classroom from the Unit 5, and I was just wondering why, because I think I think I did pretty well on that, and it was late, but I did email you and ask if I could use my 504 for an extension. So I
Yeah.
was just wondering.
Yeah, it depends upon your score because the AP classrooms are graded both on completion and
And your score.
some degree of accuracy. So
Okay.
I'll have to go back and look and see what you
Okay.
got, and maybe it was a grading error, and so I'll look
Okay.
into it. Okay.
Okay. Thank you so much.
All right. Talk to
Okay.
you.
Bye.
Bye.